This chip can perform roughly 1,000 trillion arithmetic operations every second. And while it is generating a word of an answer for you, it is doing almost none of them, because it sits idle for something like 99.7% of the time it is switched on. Now, that is not a broken chip, and it is not badly written software. What you are looking at is the ordinary, well-optimized behavior of every large language model running anywhere in the world right now. So what are you actually paying for when you use one of these things? Not arithmetic, it turns out. You are paying for a walk out to memory and back, once for every single word. And the walk is so much slower than the arithmetic that the arithmetic may as well be free. And if you wanted to make it faster, the obvious answer, a faster chip, is the one thing that would not help you at all. The quantity that explains all of this is called arithmetic intensity, and it is the plainest ratio in the whole field. How many arithmetic operations do you perform for every byte you read out of memory? Every chip has its own version of that number, and you can work out an H100s in one division. It performs about 990 trillion floating point operations a second and reads memory at 3.35 terabytes a second. So divide one by the other and you get roughly 295 operations per byte. That is the exchange rate the hardware is offering you. Feed it work with more arithmetic per byte than that, and arithmetic becomes your bottleneck. Feed it less and memory does. So for the next 20 minutes, you and I are going to find out exactly where token generation sits on that scale, why it sits there rather than somewhere more sensible, and what the two most interesting fixes of the last 3 years have actually done about it. Here is that exchange rate drawn as a picture, and the picture has a name. It is called a roofline. Along the bottom you have arithmetic intensity, operations per byte on a log scale, and up the side you have how fast the chip actually manages to run. On the left, the line rises, which means you are memory bound and the only thing that helps you is reading fewer bytes. On the right, it goes flat, which means you are compute bound and the arithmetic is finally what limits you. The corner between those two regimes sits at 295 operations per byte, and I would like you to hold on to that number, because everything else in this video is measured against it. Now look at where the workloads land. Training a model sits comfortably out to the right on the flat part, which is where all the talk about petaflops comes from. And generating a single token does not land anywhere near it. So where does generating one token actually land? Let us work it out together, because it is 2 lines of arithmetic and the answer is the entire video. To produce a single token, the model reads every one of its weights exactly once. And for each weight, it performs 2 operations, one multiply and one add, while each of those weights, stored at 16-bit precision, costs 2 bytes to read. 2 operations, 2 bytes. So you are doing 1 operation per byte. And the corner, remember, is at 295. So token generation is not slightly memory bound and it is not sitting near the edge of anything. It is memory bound by a factor of about 295, which means the arithmetic units you paid for are busy roughly 1/3 of 1% of the time and idle for all the rest of it. And that ratio does not care in the slightest how good your code is. The first 2 comes out of the mathematics of a matrix multiply, and the second comes out of your choice of number format. So the only levers anybody has are to read fewer bytes or to do more arithmetic with each byte once you have read it. But why would anyone build a chip so badly matched to the job? They did not, and this is the part worth sitting with. The very same chip, doing the very same job at training time, sits out on the right of that corner and uses its arithmetic properly. Because a training step pushes thousands of examples through the weights at once, and every byte you read gets thousands of operations done with it. So the chip is not mismatched to the workload at all. It is beautifully matched to training, and inference is simply the other workload, the one nobody designed it for. Which brings us to the obvious fix, and it is the one that everybody uses. If the trouble is that one token's worth of work does too little arithmetic per byte, then you serve many people at once. Read each weight a single time and use it for 32 different conversations before you throw it away. Now watch what that does to the ratio. The bytes you read stay exactly the same, because they are the same weights either way, while the arithmetic multiplies by the batch size, so your intensity climbs from 1 operation per byte to 32, and the chip's utilization climbs with it. And that is why a token gets cheaper when a model becomes popular, and why almost every serving system in the world is quietly waiting a few milliseconds before it answers you, just to see who else turns up. But batching does not carry you all the way to that corner. So what stops it? It is the one part of the model that nobody can share. Every conversation drags its own history along with it. For each token already sitting in the context, the model has stored 2 vectors, a key and a value, and it rereads every one of them in every layer each time it produces the next word. That store is called the KV cache, and here is the asymmetry that matters. The weights get read once and used by everybody in your batch, but each conversation's KV cache gets read once and used by exactly one person. So as you add conversations, the weights amortize beautifully, and the KV cache does not amortize at all. It is the part of the read that grows with your batch size, instead of being divided by it. So how big does that cache actually get? We can compute it exactly, and we can do it straight from the model's own published configuration file, which is a thing you can download in a browser in about 10 seconds. Take Qwen3, the 32 billion parameter one, 64 layers, 8 key value heads in each layer, every head 128 numbers wide, 2 vectors per head, 2 bytes per number. Now watch what happens when we multiply that out. A single token of context costs you 256 kibibytes. Which sounds harmless and is not, because you pay it per token, and this model will happily accept 40,960 of them. So fill its context right up, and the cache for that one conversation is 10.7 gigabytes. On a card that holds 80 gigabytes in total, and has to fit the model itself in there as well. Now look at what that same model would have cost you if it had been built the obvious way. Qwen3 has 64 attention heads, but only 8 key value heads, which means groups of 8 heads are sharing a single key and value between them. That sharing is called grouped query attention, and it is now in essentially every model you have heard of. So what if we take it away? Give every head its own key and value, exactly as the original transformer did, and the same context costs you 8 times as much. 2 mebibytes for every token instead of 256 kibibytes. And at full context, that comes to 85.9 gigabytes for a single conversation, which does not fit on an 80 gigabyte card at all, before you have loaded one weight of the model you were trying to run. But I want to be careful with that 85.9, because it is a counterfactual rather than a real model. What we computed is what Qwen 3 would have cost if its authors had made one different decision, worked out from their own configuration with a single field changed, and nobody ever shipped that model. So why show it at all? Because the size of a saving only means anything measured against the thing it replaced, and this is the honest way to state one. Not that grouped query attention is efficient, which is vague enough to be unfalsifiable, but that this model at this context length needs 10.7 gigabytes where it would otherwise have needed 85.9. And you can check that yourself in about a minute with the file they published. So sharing buys us a factor of 8. Can we do better than sharing? And in 2024, a group at DeepSeek answered it with something rather more interesting than I expected. Their idea is that a key and a value do not have to be stored as a key and a value at all. You can compress the pair of them jointly down into one smaller vector, a latent, and store only that, then reconstruct whatever you need on the way past. They call it multi-head latent attention. And the compression is not some lossy approximation bolted on after training. It is trained as part of the model, so the network itself learns to put into that latent whichever information it is going to need later on. Now watch what that does to the number. DeepSeek v3 has 61 layers. Its latent is 512 numbers wide, plus another 64 for the positional part, which cannot be compressed, at 2 bytes each. That comes to 70,272 bytes for every token, or about 70 kilobytes. And I derived that from their configuration file rather than lifting it out of the paper, and it agrees with the paper exactly, which is the nicest kind of agreement you can get. The number they published falls straight out of the architecture they published. So how much does that save us? Now compare it against the same model built with full attention, every head keeping its own key and value, 3.81 megabytes per token. 57 times larger for the same model at the same context, off the back of one design decision. And measured against a real competitor rather than a counterfactual, the gap is still large. Llama 3.1 at 405 billion parameters and using grouped query attention stores 516 kilobytes per token, where DeepSeek v3 stores 70, so 7 1/3 times smaller, on a model that is in the same conversation about capability. Now, you will sometimes see this quoted as a 93% reduction, and that figure is perfectly real. But it is measured against something quite specific, DeepSeek's own previous dense model, not against anybody else's. So why labor the point? Because the difference matters enormously if you are comparing one lab against another, and because a number detached from whatever it was measured against is not really a number at all. Now look at what we have actually optimized over the last 3 years. Almost none of it was the arithmetic. Hardly anything anyone has done to these models has been about making the multiplications go faster, for the straightforward reason that the multiplications were never what you were waiting on. Grouped query attention reads fewer bytes. Latent attention reads fewer bytes. Quantization, storing your weights in 8 bits or 4 instead of 16, reads fewer bytes, and speculative decoding reads the big model's bytes less often by guessing ahead with a small one. 4 techniques that look completely unrelated when they are listed on a slide, and every single one of them is the same move. Shrink the denominator and slide to the right along that roofline, which is why this problem has been called the memory wall for a long time, and why it has nothing much to do with language models. Arithmetic has been getting cheaper faster than memory bandwidth has been getting cheaper for about 40 years now. So the ratio between the two keeps widening, and every new generation of hardware pushes the corner on that roofline further to the right. Now think about what that does to a workload sitting at 1 operation per byte. What would you buy to fix it? A faster chip does not help you. A chip with more arithmetic units does not help you either. And the only 2 things that do help are more bandwidth, which improves slowly and expensively, or reading less, which is a question about the model rather than about the machine. There is a practical consequence here that you can actually go and observe for yourself. The first token of an answer and the 10th one are produced by 2 completely different kinds of work. Reading your prompt is a compute-bound job because all of those tokens go through the model together. So the arithmetic intensity is high and the chip finally gets to run properly. Generating the reply is the memory-bound job we have spent this video on, 1 token at a time, all the way down. So why does a long prompt cost you less per token than a long answer on essentially every provider's pricing page, and why are the 2 billed as separate line items at all? Because we are being charged for 2 different regimes of the same machine. The price list is a roofline written out in dollars. I want to finish on the part of this I find genuinely strange. We have built an entire industry on chips whose headline specification is arithmetic, and the workload that industry actually sells you, a model answering a question, uses about 1/3 of 1% of it. Every serious efficiency result of the last 3 years has really been an argument about bytes, dressed up in the vocabulary of attention mechanisms. And the wall is not going anywhere, because the gap between arithmetic and bandwidth has been widening since long before any of this existed. And nothing about the shape of a transformer makes it narrow again. So the question I keep coming back to is not how much faster the chips are going to get. It is what a model looks like when somebody designs it, from the very first line around the cost of reading it